Hi, good morning, everyone. I am Dr. Vithanage. I am from Department of Mathematical Sciences, Wayamba University of Sri Lanka. So today I'm going to teach a lesson about analyze real-world incidents using mathematical models of ordinary differential equations. So mainly we know that we can analyze real-world happenings or real-world problems by using the concepts of ordinary differential equation. So let's see about what is an ordinary differential equation. So the basic idea of an ordinary differential equation is it is containing a function of one independent variable and its derivatives. So if we look at this example, we can see that here x is the independent variable and the derivative is dx over dt. So we use ODE to abbreviate an ordinary differential equation. Basically, ordinary differential equation has main two factors. One is the degree and the order. So when you consider about the order of an ODE, it is the highest order derivative it contains. So the degree of an ODE is defined the power to which the highest order derivative is raised. If we look at this example, we can see that the highest order derivative is b square x over dt square. So it is 2. So this has order 2. And we consider about the degree, it is the power of the highest order. So it is 1. So considering about the geometrical representation of the derivative, or what is the real idea of that? It is the increasing rate. So if we encounter an increasement or decreasement, we can represent it by using the derivative. So if we look at in our real world applications, velocity is the rate of change of the displacement, and acceleration is the rate of change of velocity. So basically, here we can see the tangent at x and f of x, that point, it is the derivative. So now we are going to construct a mathematical model for an object falling under air resistance. So we know that in our day-to-day life, coconut plant or some apple or anything is falling from the sky. So in such situation, we want to observe about its motion, especially the velocity. So mainly air resistance is working to upward and the gravitational force is working to downward. So we can model it by using f of t is equal to n. So here ng is the force due to the gravitation and k of v is force due to the air resistance. And it is equal to m times a. As we learned previously, this a is the acceleration. It means it's the rate of change of the velocity. So now we have construct our mathematical model. Then we need to solve this mathematical model. Simply, this is a differential equation. So here we use variable separable method. It means we take all the v variables in my left-hand side and t variable in my right-hand side. Then I have solved it. So finally, I can obtain an answer for v. It means I have isolated an expression for v. Then I can use the initial condition, that is when t is equal to 0. It means when we start to measure the time, the speed of this coconut plant is equal to 0. Then we can find the value of the constant and it is equal to g. So here we have obtained some expression for the velocity. Then we can find the equilibrium points by equaling this derivative to 0. So it is v is equal to mg divided by k. So equilibrium point means there is no any change in the velocity. In such time, the gravitational force and the air resistance on this object is working equally for different directions. So then we can plot this motion, the velocity with time, by using MATLAB. You can see that it is increasing. Then after that, it is some 6 level. Then let's look at the mathematical model for the motion of a simple pendulum. We have learned this phenomena in our advanced levels also. Here we use the angular version of f is equal to ma. So it is tau is equal to I alpha. Here I is the angular inertia, and alpha is the angular acceleration. So here theta is measuring angle, it means the displacement. And here we can see that our mathematical model, we have obtained a second order differential equation as we are considering about a small motion, sine theta is equal to theta. Then we can solve this equation for theta. Then I linearize this equation system by using two variables. X1 is equal to theta and x2 is equal to theta dot. Here I have obtained the equilibrium points by equaling this x1 dot is equal to 0 and x2 dot is equal to 0. Then I can see that 0, 0 is the equilibrium point. It means when velocity is equal to 0, its displacement also equal to 0. So now I have drawn the plot of this motion of this pendulum with respect to time. We can see that it is a sine motion. It means it is increasing, again decreasing and increasing like that way. It has some sine curves. Then I am going to discuss about a mathematical model to study the relation between rising atmosphere temperature and human population. As we know, in the present world, rising atmosphere temperature is a burning problem. So mainly we can analyze this problem by using a simple mathematical model by using ordinary differential equations. Here X is the population density and Y is the rising of atmosphere temperature. By using these two variables and some ideas from the books and internet, we can construct our mathematical model. So XY is proportional to the rate of change of human density, and XY is negatively proportional to the rate of change of the rising atmosphere temperature. By using these two ideas, we have obtained our mathematical model. Now this contains two ordinary differential equations. Here B and D are some parameters. B is the rate of global warming by human activities. And D is the decreasing rate of human population due to climate. So first we can obtain the equilibrium points. It is dx over dt is equal to 0 and dy over dt is equal to 0. Then I can clearly obtain that 0, 0 is the equilibrium point. So biologically, it means that when human population is 0, atmosphere temperature doesn't increase. It means when there are no humans, this atmosphere temperature is a constant level. So now we can analyze this mathematical model by using numerical analysis. So basically using MATLAB, I have plotted the graph. So you can see that this red curve represents population density, and also this blue curve represents the increasement of the atmosphere temperature. So if you predict for next 500 years, we can see that human population density is decreasing according to our mathematical model, and atmosphere temperature is increasing little by little. So finally, we are going to consider about mathematical model treat for cancer. So we know that cancer is a burning issue in the modern world. Mainly, millions of people are suffering from this cancer. The idea of the cancer is it is a disease in which some of the body's cells grow uncontrollably and spread other parts of the body. So in the world, there are a lot of treatment methods, immunotherapy, chemotherapy, such kind of popular treating methods. So here we consider about immunotherapy. It means immune cells in our body act as the fighters. So here we are going to construct a mathematical model that these immune cells are fighting with cancer cells. For this fight, now we are going to construct our mathematical model. So here X is the tumor cell population and C is the immune cell population. So now in our mathematical model, it contains mainly two state variables, X and Z. Then here R is the growth rate of tumor cells, and D is the inverse carrying capacity of tumor cells, and S is the supply rate of immune cells, and D is the rate of immune cells by tumor cells. Now, first we are going to find the equilibrium points of the system. For that, we equal X prime and Z prime to 0. So you can clearly see that it contains two equilibrium points. So one equilibrium point is cancer component is 0. So it is a cancer-free equilibrium point. It means in that case, there are no cancer in human body. And on the other hand, positive equilibrium point means in that time, cancer component has some fixed value. So we symbolize it as X star Y star. Now we are going to consider about the existence of equilibrium points in each case. Here we must consider null clines. The idea of the null cline is when x prime is equal to 0 and z prime is equal to 0, we are drawing the plots. So you can see that we have obtained two expressions. C is equal to r times 1 minus bx divided by k, and c is equal to s divided by b minus mx. So now we are drawing geometrically. So there you can see that when s divided by d is greater than r divided by k, it means simply the supply rate of the immune cells is greater than the growth rate of the cancer. There are no positive equilibrium points. So it means in that case, cancer can be removed. And on the other hand, in the second graph, you can see that when the supply rate is low and this tumor is growing fast, so it has one positive equilibrium point. These intersections represent the positive equilibrium points. Now let's consider about the periodic solution. So periodic solution means when the solution curves behaves periodically, it is called a periodic solution. It means again and again that curves come to the same position. So it can occur repetitions. And also we need to show that the system doesn't contain periodic solution. Here we use the G.V.R.K criteria for that. So by using this G.V.R.K criteria, we can show that according to this operator, if it is positive or negative in a simply connected region, then there are no periodic orbits. So here, this is always negative. So it means the system doesn't contain periodic orbits. So biologically, this means that cancer will not occur again and again. So now we are going to analyze about the stability of the equilibrium point. We can see that how stability of equilibrium point we can study. Here, stable node means all the trajectories attracting to cancer, attracting the equilibrium point, and stable spiral also the same. An unstable node means these curves are going outward from that equilibrium point. So you can see it in red color. So now we are going to discuss about the stability of the equilibrium point. So first we need to calculate the Jacobian of the matrix. Then we have found it. Then we find the eigenvalues by substituting that equilibrium point into that Jacobian. So here, if we consider the cancer-free equilibrium point, we can see that as it is a lower triangular matrix, so we can use the diagonal become the eigenvalue. So if R is less than S times K divided by T, it means both eigenvalues are negative. It means cancer can eliminate completely. But when R is R minus S K divided by D is greater than 0, it means one eigenvalue is positive. So it is a saddle. It means this is not stable. So cancer-free equilibrium point is unstable. In that situation, we can say that we can remove the cancer. So finally, let's consider about the positive equilibrium point. Here we can obtain that here the determinant is negative and the diagonal when we consider trace is negative and the determinant is positive. So it is locally asymptotically stable. So the final result is when S divided by D is greater than R divided by K, there are no positive equilibrium points, and tumor we can remove the cancer completely. And on the other hand, when the supply rate is less than the growth rate of the tumor, cancer-free equilibrium point is unstable and positive equilibrium point is stable. It means cancer must be fixed in some level. Okay, so here we can see that how we can find a treatment method by using this ordinary differential equation. So it means we need to increase the supply rate of these immune cells greater than the growth rate of the tumor. So do you have any questions you can ask from me? Okay, thank you. And these are my contact details.